So, today's learning targets. I can explain what a power function is, and I can identify the constants and power of power functions. This is the more important of the two, the second one. Ready? So, power functions are equations that can pretty much be written in this form: k times x raised to the a. All right? And I will explain what that means in just 1 second. All right? So it is f of x equals k times x to the a. So, what do all these things represent? Well, k is a constant of variation. That's some constant, and it's not a variable. It is a constant, okay? A is the power of x. It's the exponent, right? And k and a should not equal 0. What happens if k is 0? Yeah, the equation's 0. If I make k 0, whatever I multiply times 0 would just be 0. We'd have no x and no exponent again, would we? Right? What happens if a is 0? What happens if a is 0? Well, a function wouldn't equal 0 altogether. If I had k times x to the 0, it would equal k. Anything to the 0 power is 1, therefore it would just equal k. We'd have no variable again, would we? All right? So, our power functions have some constant times our variable raised to an exponent, where our constant and exponent both cannot be 0. So we are going to figure the power and the constant of variation. So basically, we're going to figure out what our a and our k would be here. All right? You don't have to remember the variables, or excuse me, the letters k and a. You just have to know which one's your power and which one's your constant. So right here, right now, circumference of a circle. We know that's 2 pi r. Can anyone guess what either the power or the constant of variation is going to be? That 2.
1.
Well, what's okay? What's what?
Huh?
What's what?
R.
R is 1. The power of r is 1. Okay, so you're saying, well, this is my variable, the radius. I don't know what it is, and it has an exponent of 1. So my power is 1. And I heard someone say constant is 2. Almost correct, the constant. It's 2 pi. Remember, my variable in this case is r. We're multiplying r by 2 pi. Pi is a number, let's not forget. It's an irrational number, it goes on forever, but it is a number. So 2 times pi is what my constant is. All right? Not too bad. What about the area of a circle? We can say k. Yeah, the power is 2. And what's my constant? Pi. That's it. Not too crazy. Until we get to the force of gravity. All right? That equals k over d squared. Now, let's not forget, k is our... That's not a variable in this case. So our force of gravity, k is the constant of variation. What is the power? What's the power there? Any guesses? Well, yeah, you can guess 2, but that is not correct. How would I rewrite this so it's not a fraction? How would I rewrite this so it's not a fraction? It's not 1/2. We know k is our constant, right? But what can I do to the denominator there to bring it up? If I negate my exponent, doesn't that flip it up by negating the exponent? It's the -2, correct? So my power in this case is -2. All right? Remember those rules of exponents. If I have a negative exponent, I have to flip it. This was -2 it was like this first, but then we flipped this down to bring it here. But if we want to figure out what the power is for the power function, we need to bring that back up. Which means Boyle's law. V equals K over P. What's my constant variation? What's my power? -1 is the power. What's the constant? Okay. There you go. Power functions. We have the graph of f of x, which is the cubed root of x. All right? So first, let's figure out what our power and constant of variation is. Anyone know what the power might be? Not cubed, because it's not x cubed, it's the cubed root of x. What's another way to write an exponent? 1/3. And how do we know that? Remember, bottoms out. If we have x to the 1/3 power, how do I write that in radical form? Yeah, the bottom goes out, right? Our bottom number is the one that shoots out. The top, down, just comes down to the x. That's it. So the power, that's the same thing as saying x to the 1/3. My power is 1/3. And now that I have it in this form, now that I have it in that form, what's my constant of variation? If I say x to the 1/3, well, our power is 1/3, what's our constant of variation? It's 1. It's the number in front of the x, isn't it? So that's 1. Now, all this other stuff is just review based on looking at the graph or looking at the calculation of our function. What's the domain? Domain or what? X values. It's all real numbers. It goes right and left forever. There should be arrowheads here. Let's get right from the calculator. Should be arrowheads there. Yeah, that goes right and left forever. So we say all real numbers. You can say from negative infinity to positive infinity, or you can just do the fancy R for all real numbers. Too bad. What about the range? If domain are all my x values, the range should be all my y's. Remember, this is my x-axis, this is my y-axis. So does it go up forever, or does it limit itself at a number? It goes up forever. That goes up slowly forever, but it does go up forever. So if it goes up and down forever, all real numbers again. Is it continuous?
Yeah.
Yes. How do we know it's continuous? Why? I can draw this graph right here without picking up my pen or pencil whatsoever. There's no asymptotes that cut it in half. There's no holes. There's no jumps. Whatever. So is it continuous? Yes, it is continuous. Increasing and decreasing. How can we tell if something's increasing versus whether something's decreasing? It's a slope, whether it's a positive or negative slope, correct? So let's take a look at this. Is there any place where this thing looks like it has a negative slope? Third quadrant. If I pick a point into the tangent line here, is that a positive or negative slope? It's positive. So is there any place where it has a negative slope? No, there isn't. So it's never decreasing. So where's it increasing? It's increasing forever, isn't it? It's increasing forever. So you can say from positive to negative infinity. Question. What is the slope at the point 0? Is that straight up and down? Because remember, if it's a vertical line, it's undefined slope, right? What do you guys think? What do you guys think? Well, if I put in the 0 for x, obviously y is 0. So there's a coordinate right here, 0, 0. At that point, is that a positive slope? It's not a negative slope. I know it's a positive slope because it kind of the slope kind of goes like this, and as it gets closer to the origin, it kind of straightens up. But is there a vertical line right at the origin? There is. Right at the origin, the slope, if I were to draw a slope here, it's a little bit positive, a little bit more positive, a little bit more positive, a little bit more, then it actually comes up, then it goes positive again, positive, a little less, a little less, a little less. So right at the origin, there's a vertical line for the slope. And that means the slope doesn't exist there, does it? So it's like increasing everywhere except at x equals 0, isn't it? So we can write that. All right? We can say it's increasing on all real numbers except at x equals 0. It's undefined. It's undefined. That's a tricky one. That's a tricky one. Is it symmetrical? See, here's this graph. Is it symmetrical? I'm hearing no's and yeses. Those of you that say no, how come you say no? Those of you that say yes, how come you say yes? So you're saying it's symmetrical over the y. Here's the y-axis right here. If it was symmetrical over the y, this would be reflected this way, wouldn't it? It's a reflection over y equals x, you're saying. Hold on, here's y equals x. We'll draw this line right here. 3, 3. That's y equals x. Does it look like it's reflected over that? Y equals negative x. So you're saying if I do it this way, it's a reflection. No, when it reflects like this, would then reflect like this. It does. So what do we say it reflects from? Is that y equals x or x equals y? The origin. It's reflected over the origin.
You did say that.
Who did? I'm sorry. Who said that a little while ago? Sleepy? Good. You would be right. I didn't hear it because I was engaging in this conversation here. Okay, it reflects, it's symmetrical, yeah, about the origin. Absolutely. And if it's reflected about the origin, what else do we know about it? Anybody remember?
It's odd.
It is odd. It's an odd function. It's an odd, therefore, it's an odd function. I know they didn't ask us for that, but this is something we learned already. If it reflects about the origin, it's symmetrical around the origin, then it's an odd function. Is it bounded? No, because it goes up and down forever. I mean, you can look right at your range. It goes up and down forever. Slowly, but it does go up and down forever. So is it bounded? No. Are there any mins and maxes? No, because there's no hills or valleys, right? There's no. Are there any asymptotes? No. And oh my God, we are done. Can't believe we did that. But we did a really good job with that. All right? Now, why don't you guys try this one? I'll give you a few minutes to do this one, and then we'll go over the answers. All right, let me add something to this graph for you guys in case you're wondering. Because I took this right off the calculator screenshot. This goes up forever and up forever here. It never connects. It doesn't connect and loop over. And this goes this way forever, like that, and this way forever, like that. So we got this. And we got, so that might help with domains, asymptotes, things of that nature. So consider that before we go over the answers. Shall we? Before we start answering these, what's another way I can write that in power function form? X to the negative 2. Okay, so this is the same thing as saying x to the negative 2. All right, so what's my power there? Negative 2. Okay. What is the constant of variation? 1, because the coefficient in front is a 1. All right, now all the good stuff. What is the domain? Well, domain are all, what are the x values? Yeah, it can be anything but 0, right? It never touches the x, or it never touches the y-axis, and it never crosses the x value of 0. initializes. So we can say domain is all real numbers except x cannot equal 0. Besides looking at the graph, looking at my original function right here, how do I know x can't be 0? Yeah, 0 can't be at the bottom. It makes it undefined, right? That's one of the ways we determined asymptotes. Oh, I stick your heads. You guys know where the vertical asymptote is. All right. So, what's my range? Correct. If I look at my graph, it goes up forever, so it goes to positive infinity. But as I come down on the y-axis here, it gets closer and closer to the 0. Yes. Yes, in a second. It gets closer to y equals 0, which is right here, but it never touches it. So it's bigger than 0 and above, right? So we say y is greater than 0. It's not equal to 0, because it never touches. Is that continuous? No, how come? Yeah, when I draw the graph, I can't draw it without picking up my pencil. It's near impossible. It's actually impossible. Unless you put a pencil in your right hand and a pencil in your left hand and draw it. Yeah, I get it. But that would require 2 pencils, not 1. Okay? So, is it continuous? We said no. Where is it increasing and where is it decreasing? Any takers? Donnell, you think you know this or no? Increasing or decreasing? Either one. Let's start with increasing. Where does this function at positive slope? Pick a quadrant. Where does it have a positive slope? Quadrant 2? Quadrant 2 has a positive slope. But how do I write that? It's increasing where? I'm sorry. Where is it increasing? How do we say that? Well, negative infinity is all this way, right? So from negative infinity to where? What value of x does it stop increasing? It's 0, right? It goes up forever. It increases all the way from 0. Here's a 0, all the way from here to forever. It doesn't touch the 0, so that's why we don't include 0 in our inequality. What about decreasing? The slope is negative in quadrant 1, isn't it? So that goes from 0, it doesn't include the 0, to where? To positive infinity, because it will increase forever. It'll be really, really, really small increase. Small positive slope, but it'll go that way forever. Symmetrical. Yes, it is symmetrical. It is symmetrical because it reflects over what? It reflects over the y-axis, which means it is an even function. It is an even function. They don't ask that, but we learned it. Is it bounded? It's bounded above?
No.
It's bounded below. Because there's a point in this graph where it does not get any lower than 0. Okay? So I would say, yes, it's bounded below. Although some people might say, you know what? It technically, it goes less than 1 to 1/2, right? I cut that in half, it goes from 1/2 to, well, a little bit more. But it gets cut down, right? When you take a half of things, keep on taking a half of things, it's never really stop decreasing. You see what I'm saying? This will constantly keep on going lower and lower as it goes further left and further right. The y value will keep on shrinking to a point. But it never really crosses the 0. So I will say that, yes, it is bounded below. That's a tricky one. In fact, because of what we just said, how it just keeps on going lower and lower and lower, I'm going to say it is not bounded. I'm going to say that it is not bounded because of what we just discussed. As it goes left and right forever, it actually keeps on lowering the y value. The y value never stops lowering. It's weird because it doesn't cross. So in order for it to be bounded, we'll say it this way, there has to be a point, a min point. There's never a minimum point here because it keeps on going lower. So I would say it's not bounded below. Okay, min and max. Well, we just discussed, is there a min point? No. Is there a max point? No. You all right, JR? Asymptotes. Asymptotes. Where there are two asymptotes. Where are they in this graph? At y equals 0. Y equals 0. Is that a horizontal or vertical line? It's a horizontal line. It's got to cross the y-axis at 0. Y equals 0. It doesn't touch 0. And where else? At x equals 0. Because it's got to cross the x-axis right at 0. There you go. So there are two asymptotes. At y equals 0, it's an equal sign. And at x equals 0. There are two. Very good. Bang.